today we're going to be doing Senior Advanced, and in Senior Advanced we're going to be learning about limits. With limits, we're going to be learning about the basics of it, graphs and tables, limits that don't exist, laws of limits, solving limits algebraically, squeeze theorem, special limits, and using the highest degree. So our first topic of limits is the basics of limits. So what is a limit? A limit is basically a prediction of any point within a graph. It could be a hole in a graph, an asymptote, or it can just be a normal point. For example, there's a hole in that graph. A limit helps us find what the y-coordinate of that is, because we know what the x-coordinate is. So how do we find the limit of a function? Well, there are many ways, but in general, each way is focusing on narrowing down the neighboring points closer and closer, so until we get to that point. And why do we need limits? Well, limits are a very important part of calculus. You'll see them everywhere, and they help us find predictions of stuff we don't know. So here I have a graph of f of x is equal to x cubed minus 1 over x minus 1. So we're going to figure out what the coordinates of that is. So we know it's 1 comma something, and that something would be our limit, the y-coordinate of whatever we don't know. So why do we have a hole here? Well, it's because the denominator of this function is x minus 1. If we were to plug in x for 1, we would get a denominator of 0, which gives us an undefined answer. And that's why we have a hole. So before we get into how to find the limit, let's do a little bit of notation. We write a limit like this. The limit of f of x as x approaches a, so x is just any value of x, approaches a, meaning it goes into a, or our x-coordinate from both sides. Remember, both sides. So here we have x approaching 1 from both sides. So from this side and that side of f of x, which is going to be our function, in this case, x cubed minus 1 over x minus 1, is equal to our limit. And our limit, like I said before, is the y-coordinate. So in general, there are two ways. Well, two ways for us that we'll start on now, and then we'll get into how to do it much quicker. So first, we have a graph. You're not going to be able to graph it every time, but if you have a graph, it's helpful. So our hole is here. And we can just see, if we kind of trace it, that it looks like our limit goes to 3, right there. Another way is using a table. And what we'll have is x and f of x, put in values of x that are close to 1, because we can't find 1 exactly, on both sides. Remember, doing it on both sides is important. That way we have a more accurate prediction. If we plug it into our function right here, we have 2.710, 2.970, our limit 3.030, and 3.310. Well, kind of looks like that they're going closer and closer to 3. If you plug in values closer to 1 from both sides, you would see that they are getting closer and closer to 3. So in this case, our limit would actually be 3. So the next thing we're going to do is graphs and tables. As you saw before, graphs and tables are useful. Well, they're not always going to be as useful because you're not going to be able to draw a graph every single time if you have like a polynomial with 7 terms. But for now, it's just an introduction to limits for us. Anyways, our problem today is find the limit of f of x is equal to x over the square root of x plus 1 minus 1, where it is undefined. Our first step is to find where it actually is undefined. That's where our limit is going to be approaching from both sides, and that's where we're going to have a hole in the graph. So what we're going to do is our limit is going to be, our function is going to be undefined if the denominator is 0. So let's solve the denominator for 0 to find where x will be undefined. So the square root of x plus 1 minus 1 has to be 0. Bringing it down, the square root of x plus 1 is equal to 1 because we add 1 to both sides. Square both sides to get x plus 1 is equal to 1 because 1 squared is 1. And then you solve for x to get x is equal to 0. And if you plug it back in, you know it's going to work. Well, work as in it's going to be undefined. And if you look at my amazing graph that I drew on the side, you can also see that our whole is at 0. X is equal to 0 right there. So let's try finding the limit. First of all, if we look at the graph, it's kind of obvious where it's going to be, at 2. Let's also try a table. I haven't filled this out, but as you can see, I chose points that are closer and closer to 0 on the negative side and the positive side. Remember, limits are important from both sides. We'll get to one-sided limits later, but for now we're doing both sides. So if you fill in the table, which you guys should do right now, you see that from both sides, our limit, or y approaches 2, which is our answer. Our next topic is limits that don't exist. Although most limits do exist, there are some that just don't, and there's 3 main cases for it. Before we get into those 3 cases, you might be wondering, what do I do when a limit doesn't exist? Well, simple. Just write D and E, which, you guessed it, stands for does not exist. Anyways, so we have 3 cases. Discontinuity, it blows up, or oscillation. You might be wondering, what are those? Well, here's a little picture. Discontinuity is when it's like weep, and then like there's like a and then weep. Basically, the point where it's undefined isn't the same. It just looks. How we test for discontinuity when you have a graph is, let's see if I can draw this without lifting my pen. So, whoop. I have to lift it to get there. So that's discontinuity. Whenever you experience one of those, there's no limit. Well, more specifically, there's no limit at this point. You can find a limit here, but there's no limit at this point. Then we have blow up, which basically this blows up. It's when it's like whoop, whoop. So there's a little vertical asymptote right here, and it just goes on to infinity. The limits don't exist. You can technically also have a blow up where it technically just blows down. Both are don't have limits. But once again, limits don't exist here. You might will have a limit here, but you won't have it there. And finally, oscillation. This is just like a spring or a yo-yo or one of those weird things on doors that you flick and it makes a really interesting noise that drives your parents insane. Anyways, it looks like this. So we have like little this, and then it goes like closer and then closer and then closer, and then it becomes the same thing. We don't have any kind of limit when we get there. So basically, going back to discontinuity, we have something called one-sided limits, meaning limits that go from one side of the graph. For example, coming from the left side or the negative side of the graph is where we write a little negative over the a. Meaning if we wanted the limit as x approaches a of f of x, we only look at what it approaches from the left side. In this case, it would approach this point, which would be our limit. But we also have, just like approaching from the negative side, it approaching from the positive side, which is like this, meaning it's approaching from the right side, from this side. And if we follow this, it will approach this. But one thing is, if we want the limit in general of that point as it approaches from both sides, it does not exist unless both are equal. If they're not equal, no limit. But if they're equal, the limit is simply what they both approach. So our next topic is the laws of limits. And basically, when we solve limits algebraically, because we don't need to use a graph or table every single time because that gets annoying and hard to do, we have these laws that we use to solve them. So basically, in this, a and c are constants. Mainly c is a constant, and a is just a variable. Anyways, the limit as x approaches c of f of x is equal to f of c if the graph is continuous. This basically means, well, it makes our whole life simpler. Basically, if we have a limit and it's continuous at that point, meaning there's no hole, all we have to do is plug it in and we get our limit. Simple. So then we also have the limit of f of x plus or minus g of x as x approaches a. That we can basically distribute like we did. So it becomes the limit of f of x as x approaches a plus or minus the limit of g of x as x approaches a. The same case goes for multiplication and division. And since they're technically two separate rules, but they basically are the same thing, I fit them both in the same thing, like plus and minus, multiplication and division. So those are two more rules. And then we have the limit of c times f of x as x approaches a. It's basically equal to c times the limit of f of x as x approaches a. Meaning we can take our constant and move it out, and then multiply it back in later. And finally, our last rule is the limit of f of x to the nth power as x approaches a can be simplified as to the limit of f of x as x approaches a to the entire power of x. Meaning basically we take our exponent out and then just find the limit and then just take power at the very end. So solving limits algebraically, well, this is possibly the best thing that could ever happen to us because, like I said before, doing a graph or table every time kind of sucks. Anyways, so when we solve them algebraically, there are mainly three ways that we do it. First one is directly substituting. For example, the first one, the limit of x minus 6 over 3 minus x as x approaches 1. All we have to do is substitute. And if you want to know why, just refer back to our first limit law. So all we have to do is 1 minus 6 over 3 minus 1 is equal to negative 5 over 2, which is basically negative 5 over 2, which gives us our answer. So that's the limit of our first one. Well, there are two more. And in both of them, we can't really do that. So this one, the next thing you always want to try is factoring the numerator or denominator. Either one usually factors out somehow. So we want to factor this out. But it's important that we still write the limit because this time we are solving it, but now we're only factoring it. And we want to make sure we know that we still have to solve the actual limit. And when we factor the numerator, you can recognize that it's x minus 1 where x squared plus x plus 1 over x minus 1. And you notice that you can cancel it out. So basically, this just goes bye-bye and this just goes bye-bye. For a thing left of x squared plus x plus 1. Now you're free to substitute. So all we have to do is 1 squared is 1 plus 1 is 2 plus another one is 3, which is our answer, 3. Finally, this one can't really factor, so we do something called rationalizing. It's a little bit different than rationalizing like we usually do, like 1 over the square root of 3 becomes square root of 3 over 3. Instead, we rationalize the numerator. So let's rationalize the numerator by multiplying it by its conjugate. In this case, it's square root of x plus 1 plus, since we have a minus here, 1. So we have to do that on both parts. That way, we make sure our equation really isn't changed. So this gives us a limit of, as x approaches 0, we get, since difference of squares, you get x plus 1 minus 1 over x times x plus 1 plus x. So let's simplify this, and we get limit as x approaches 0. So technically, this just cancels out to x, and then we can just cancel out this x here with these x's. So that gets canceled out, that gets canceled, and it's a bit messy, I know, but we are left with 1 over square root of x plus 1 plus 1. Don't forget that plus 1 from when we canceled out that x here. So now we're free to substitute. So we have 1 over the square root of 0 plus 1, which is 1. And then plus another 1, 2. So our answer becomes 1/2. So the next thing we have is squeeze theorem, which is really weird but kind of useful. And it's very complicated if you just hear what I'm going to say, but if you see it in action, it's so much easier than people make it sound. But basically what it says is if you have one function, and then another function, and then a third function, and the first function is greater than equal to this function, which is also greater than equal to this function, but then the limit of this function and this third function are the same, that means the limit of the inside thing is the same as the limit as the things on the side. That sounds very complicated, and I'm pretty sure you did not understand anything I just said. So we'll do a problem. Marker. So basically, we also want to work from the inside out, like small and then go big. And we basically use squeeze theorem for trigonometric functions. So you'll see what I mean. So basically, we're going to start off with the cosine. Basically, what do we know about cosine? Well, one major thing about cosine is that its graph goes like this, meaning it's always going to be between -1 and 1. So let's start there. So we have cosine that's always between -1 and 1. And you also know that cosine of 4 over x, so let's add that, is also always going to be between -1 and 1 because you don't change the period, you don't change amplitude, you don't do any of that. You're literally just doing this, which doesn't change anything. So, yeah. And then let's work in this 5. So what we're going to do is we're going to multiply this entire thing by 5. So we have 5 cosine 4 over x. I just realized I wrote -1 both sides. I'm smart. Anyways, now let's work in the next part, this e. It's literally just going to be e to the -5 is less than or equal to, oh, I forgot that e over there, 4 over x, which is less than or equal to e to the 5. So now we've worked in all of that. Now we can work in the 3x. Technically, we don't have to do it one at a time, so we get 3x e to the -5 less than or equal to, I almost forgot to add that. I made an orange. 3x e to the 5 cosine 4 over x. Now, the last step is to literally just find the limits of these two. So, I'm not going to write it out, but the limit of this, all we have to do is substitute 0. It's going to be 0 because you have to substitute 0 there. And then we have this function, which I'm not going to write again. And then we have the limit of this, which is also going to be 0. And basically, remember what I was saying about if the limit of this thing is also equal to the limit of this thing, then the thing in the middle is equal to the limit of both things. Well, that's basically it. Meaning our limit becomes 0. So that sounded a bit confusing, so let's walk through it one more time. We're going to use squeeze theorem to carefully work our way from the inside out. We start off with cosine of 4 over x, which is between -and 1, and that's a fact, no matter what, because that's the behavior of the cosine function. And then we're going to work in our next thing by multiplying a 5 to the entire thing. So then we get 5 cosine of 4 over x, which we got this exponent. And then we're going to take the entire function to the e power. So e to the -5, you get this, and e to the 5. And then we're going to multiply by 3x. So we get 3x. This function appears, and then 3x to the e to the 5. Then we're going to find the limits. So find the limits. And then to find the limit, all we have to do is plug in 0 because we can plug in 0. Also, I forgot to mention you can't plug in 0 here because 4 over 0, undefined. Anyways, so we plug in 0 because we can, and then we get 0 and 0. And that basically means if the limit of this is in between 0 and 0, there's no other thing it can be than 0. So that's our answer. Our next topic is special limits, and there are 3 that you should memorize, especially the first one that I put a bright orange star next to. In case you can't see that bright orange star, it's this one that you should memorize. Anyways, basically the limits are the limit of sine of x over x as x approaches 0 is 1. The limit of 1 minus cosine x over x as x approaches 0 is 0. And finally, the limit of 1 plus x to the power of 1 over x as x approaches 0 is e. Now, these are all useful ones you should memorize, especially the one that I just put a giant orange box around. Memorize it. Anyways, let's try some examples. So the first one is the limit as x approaches 0 of sine of 3x over 3x. Basically, this isn't saying sine of 3 times x. This is saying the sine of 3x, like that. So, how do we solve this? Well, going back to here, since technically x in this case is 3x and they're both the same, our answer is just 1. And this marker is bad, but whatever. So, the next one is the limit of sine of 4x over 3x as x approaches 0. Well, you might be wondering, wait a minute, how are we going to do this? Because this isn't a 4. Well, here's how. We're going to do a little bit of cheating. Technically, it's not cheating, but kind of is. So, what we're going to do is we're going to sneak in. We want to get rid of this 3 and add a 4. So, we're going to sneak in a 3 over 4. Okay? But at the same time, we have to unsneak that 3 over 4. So we're also going to multiply it by 4 over 3. So it's technically the same. So this gives us, I'm just going to write it down. This gives us the limit as x approaches 0 of sine of 4x over 4x times 4 over 3. And because of our limit rules, we can bring this on the outside. So then our answer becomes 4/3 times 1, which gives us an end result of 4/3. And for our last topic of today, which is limits using the highest degree, here's how we do it. So basically, it's when we want to find the limit of a function as x approaches positive or negative infinity. And in this case, our function is just going to be a rational function, which is a times x to the power of n. N stands for the numerator's highest degree. Remember, n is the highest degree in this entire thing, all the way to c, which is our constant. And then we also have over b x to the power of d. D stands for the highest power of the denominator, all the way to e. C and e are both constants. So basically, what we do is if you have a limit as it approaches positive or negative infinity, all you have to do is compare the highest degree of the numerator and the denominator. For example, if the highest degree of the numerator is greater than the denominator, then that means your entire limit approaches either negative infinity or positive infinity based on the sign of the entire rational function. If the numerator's highest degree is less than that of the denominator, then your limit basically goes down to 0. And I'll explain why this all makes sense in a second. And then we have if the limit of your numerator is equal to the highest degree of your numerator is also equal to the highest degree of your denominator. Your limit is basically a over b. In this case, which is basically the fraction of the constants in front of the terms with the highest degree. So let's think about this for a second. If we have the highest degree is greater than the lowest degree, if you think about it, they're both growing exponentially, but the numerator is growing at a higher rate than the denominator. Eventually, the numerator is growing at such a high rate compared to the denominator, since its power is much higher, or just higher in general, that you're eventually just going to have a fraction that just goes all the way to infinity. It's not going to even be a fraction. It's probably going to be a mixed fraction. Anyways, if your denominator is smaller, if you think about it, you're going to get a fraction with a larger and larger denominator this time, instead of a numerator. And as you get a larger and larger denominator, you're also going to 0. Finally, if the numerator is equal to the denominator, well, not the degrees are equal, then that means, well, the constants as you go. This one's kind of hard to explain, but if you think about it, if you visualize it, the constants is just like a fraction that it's gonna go into. So there you go.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrical.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email, but without the info and the end. So bye!